I am eager to get going because we have a lot of really interesting material today. Once again, I apologize for the fact that I do not realistically think that future presidents need to know about relativity, except in general because it's such a fascinating thing, and real future presidents are all very curious people. So what we discussed last time was time dilation, the fact that when I'm moving near the speed of light, as you pretend I am now doing, move near the speed of light, but I'm not showing time dilation. Why not? Because I haven't turned it on. Let me turn on time dilation. And for me, time was going exactly the same speed. But for you, it was slowed down. The amount of time that I existed was much less. It slows down by this factor called gamma. So if I'm not moving at all, gamma is 1. It's not slowing down at all. If I'm moving a quarter the speed of light, then it's slowing down by a factor of 1.03. That's about a 3% slowdown. Just put in the, okay. Everything should go in the envelopes, including the ones that weren't filled out, because they don't want me filling out the spares. If you're going 99% the speed of light, then you're slowed down by a factor of 7. That's dramatic. You will, if I'm going that fast, you will time me and say, oh, he's gone for 7 years. And when I come out, I'll only be 1 year older. I will have experienced less time. This is amazing, as they say, amazing but true. Why is it true? We've discussed that before class. Why not? I mean, there's no good answer to that. These are the equations, the way the world works. Maybe we wouldn't exist today if not for this, because of some of the consequences I'll be coming to. Length contracts. So, you know, when I'm moving at 99% the speed of light, I am actually 7 times thinner. I look like a pancake. It only contracts in the direction I'm moving. The sideways directions don't change. A sphere becomes a pancake. It doesn't think it's a pancake. In its frame of reference, it hasn't changed. You have changed. You have become pancakes. This leads to a famous paradox. Think of it as the train in the tunnel. A train's coming along real fast, and because it's going so fast, it gets short. It goes through a tunnel. The tunnel isn't very long, but this train's going so fast, it fits inside anyway. As soon as it's inside, you close both of the doors, the train is trapped inside the tunnel. But now let's analyze it from the point of view of the train. Here you are going really fast, and you're not shortened up at all. In fact, in that frame of reference, the tunnel is coming towards you. Not only that, but the tunnel is super short. So from the tunnel point of view, the train has gotten short, and it will fit inside. From the train point of view, the tunnel has gotten short. How can you possibly fit inside? And yet when the doors close, is it inside or not? This is one of the more famous paradoxes of relativity. And these paradoxes really work because the fact is relativity is self-consistent, but you have to consider everything. So how could this possibly be true? Does it get trapped inside or not? Well, people forget one of the other aspects of relativity, which is simultaneity. I didn't use the word simultaneous in describing this paradox. What I said was you close both doors. If I said you close both doors simultaneously, you might have been keyed to what is the paradox here. Because if you close them simultaneously in this frame of reference when it's trapped inside, they're not closed simultaneously here. In fact, what happens is you close this one first and then this one second. So there may be no, what happens is you close this one first and this thing goes forward, crashes into the door unless you stop it. But if you stop it, then this is the thing that's moving. If you stop it, then it expands back out. I'm not going to ask you to explain this paradox on any exam. When I teach this in a physics course, I do require that of them. And then I spend really half of a lecture on it, working out the math and showing that the simultaneity makes up for the difference. I want to give you a little bit of a flavor for what's going on. Whenever you get a paradox in relativity, it's almost invariably the fact that you're intuitively assuming that things that are simultaneous really are simultaneous, whereas the concept of which came first depends on your frame of reference. So let me just quickly describe this. I'm not going to ask you to do this. This is just for your own, fun. Train, let me go over it again. train in the tunnel. It's a long train. Maybe it's longer than the tunnel. But if it's going super fast, Lorentz contracted by a factor of 7. Instead of it being 700 meters long, it's only 100 meters long. It's contracted. So here it is, really short, and it fits inside easily. You simultaneously close both doors. It's on the inside. What happens then? Well, it's more complicated if we try to stop it, because if we try to stop it, it will suddenly expand and smash out both doors. If we let it go, it'll smash into this door. We can do either way, let it go or stop. In either case, it smashes into this door. Now let's look at it from the point of view of the train. It's a full 700 meters long. This tunnel is moving towards it. The tunnel is now very short. It's Lorentz contracted. It's no longer 700 meters long. It's only 100 meters long. It's going to, here you are in the train, and this tunnel is coming towards you, and there's no way you're going to fit inside of that. So what happens? Well, the front enters. And then it comes over here, and we'll take the scenario where we don't stop it, because that's easier to think about. And then it smashes into this side. Pops out. The back comes in. Meanwhile, this smash has already taken place. The back comes in, and this door closes. The same series of events occurs in both reference frames. The front is inside. The back is inside. This door closes before the front hits it. This door closes after the back is in. Those are the same events. But the description of an event of the whole thing, which is spread out over space, does change, because events that are simultaneous in one frame won't be simultaneous when looked at in the other frame. So in this case, the thing is inside before it smashes the left. In this case, it was never totally inside, because we're talking about two separate events at two different locations that, in this case, were simultaneous. In this case, they still happen. They're just not simultaneous. That's the fastest lecture I have ever given on the train paradox. And that's why I don't require you to know it. On the other hand, it's kind of fun to be able to say those words. Just listen on the podcast. While you're working out or whatever you do. When you're listening to the podcast, you can listen to that over and over again until you can repeat the words, and then you can dazzle your friends with it. Oh, here's an interesting case. This I find particularly fascinating. Let's not take Alpha Centauri. Let's take some other star, Sirius, or some other star. I'm not sure. I want a star that's 7 light years away. Okay? I'm not sure which one that is. Sirius may be 7. The closest star, Alpha Centauri, is a little over 3 light years away. 4, I think. Let's take a star at 7 light years away. And how long is it going to take me to get there? Let's say I go at 99% the speed of light. And I'm going 7 light years. A light year is how far light travels in a year. So it's a measure of distance. It's not a measure of time. It says year in it, but it's how far light goes. It's a measure of distance. So if it's 7 light years away and I'm going near the speed of light, I'll take about 7 years to get there. Listen to this example. There's a star, 7 light years away. I'm going to go at near the speed of light. It'll take me 7 years to get there. But I'm going super fast. I'm going at 99% the speed of light. So my time is slowed down by a factor of 7. Oh, yeah, someone else has to take care of those now. No, I can't see them, touch them. They got to be delivered or mailed or something. Not that I could tell from the weight what they say, but so here we are, the scenario. The star is 7 light years away. I'm traveling there near the speed of light. I have a gamma of 7. My time is slowing down by a factor of 7. When I get there, I will be 1 year older. Okay? And here I land in the star. I stop. I say, wow, I'm here at this star. I never thought I'd get here in a year, but here I am. Isn't that great? Now let's look at it from my point of view while I'm traveling. Here I am, and I'm sitting in the spaceship, and I say, well, it doesn't feel like I'm moving. Well, that Earth is zooming away real fast, and those stars are coming to me really fast. I'm just sitting here watching my clock. Well, everything else is moving at 99% the speed of light. This is the analysis from the point of view of the moving frame, my rocket frame. Everything is moving towards me. Now, here's an interesting thing. We went to the trouble to lay out a big measuring stick between me and Sirius, or whatever star it is that's 7 light years away. In this moving frame, the sun and Sirius, with this big measuring stick between it, are moving at 99% the speed of light. There is a Lorentz contraction. This is a remarkable thing. As soon as I'm going 99% the speed of light, Sirius is no longer 7 light years away. Now it's 1 light year away and moving at me at near the speed of light. Think about this. I'm using Lorentz contract. First time through, I used time dilation and took it from the point of view of the Earth-Sirius system. Now I'm taking from the point of view of the rocket system. I'm not moving. The stars are moving, but the distance between them is 1/7 as big. It's coming at me at near the speed of light, and it's only a light year away. How long does it take for that star to reach me? About a year. When it reaches me, I jump on the star, well, the planet around the star, I don't want to burn, and I say, it took a year. What I want you to get from this are 2 different ways of thinking about it. 2 that seem completely different analysis of what's going on. In both cases, I get to that year, to that star when I'm 1 year older. I have my birthday party and celebrate 1 more year of birth. That's an event. Everybody knows around the universe that I am 1 year older when I get to that star. I can mark it down. There's no ambiguity. But I analyze it from a completely different reference frame. This is the case in relativity theory. It sounds contradictory. It sounds like there are paradoxes. When you do it carefully, you find there are no paradoxes. Well, unless you define a paradox as a seeming paradox, something that looks like it doesn't make sense until you look at it deeply. And that's the way mathematicians like to define the word paradox. Something that has an impression. They call it an antinomy if it's really a problem. But in relativity theory, it turns out there are no problems. They can all be answered. It's all completely self-consistent. It's truly amazing. And it takes a while before you get comfortable with this, before you realize it doesn't matter what reference frame you're in. It's like when I ask you, what's your velocity? And some of you say 0, and some of you say 30 kilometers per second. There's no paradox there. It's all a matter of what reference frame you're using. I even hate to say the word people in different reference frames disagree. They don't disagree. When I ask you what your velocity is and you say 0 and the person next to you says 30 kilometers per second, you're not disagreeing. You're using different reference frames. Well, how about using your own reference frame? Well, what do we mean by your own reference frame? The frame at which you're at rest? You're in every reference frame. If a bullet is moving past here, do I have to do all the analysis from the frame of rest of a bullet? No. So we all exist in all reference frames. We all experience time and distance. How long is this yardstick? The answer is, well, it depends on your reference frame. Just like when I ask you what your velocity is, it depends on your reference frame. I am not going to ask you to explain this on the final exam. This is too much, too quickly. What I want you to do is to have a sense that there are no contradictions in relativity theory, but that if you don't understand relativity theory, it's easy to find things that appear to contradict each other. But now I want to go on. These are the time, simultaneity. I mean, what do I want you to know? I want you to know there's Lorentz contraction by factor gamma. You don't have to remember the equation for gamma. I'm not going to have you memorize equations. I want you to know that gamma, however, that there's no Lorentz contraction when you're at rest. That's called your rest length. There's no time change when you're at rest. Nothing's changed. You refer things to being rest. That's a gamma of 1. I want you to know that when you get near the speed of light, gamma goes up towards infinity. So you slow down a lot and you contract a lot from the lab reference frame. From the moving frame, just the opposite. The fact that there are opposites lead to apparent contradictions, but they're always resolved when you look fully at relativity theory. Now, so far we've talked about length and space. That's what relativity theory really is. In the first step, Einstein is saying length and space, which was never really considered part of, that's like saying when you're doing a calculation, you want to do it in a pencil or a pen because you'll get a different answer. What? Oh, what? No, that's just a tool. Well, in relativity theory, the answer you get depends on the reference frame in which you do it, but there's a complete consistency. in the answers. Just like with your velocity. Now, having done this, and in the past people used to think that time and space were not something that was in the realm of physics. It was given. Here is space, and here is time. And physics simply describes how things move through space over time. The idea that time depends on the reference frame was never part of physics. Einstein's great innovation here was to bring time and space into the world of physics and to say that these things change. And that is absolutely mind-blowing. Yes? Well, we have two reference frames here, one where the mountain's at rest, one where the train is at rest. And you say there's an observer in yet a different reference frame. Presumably in a car that's going at a different velocity, but not as fast as the train. Is that what you mean? No, they're all true. The question is, doesn't one reference frame have to be true? No, there is no preferred reference frame. These events are all absolutely true in every reference frame simultaneously. Are you moving 0 or are you moving 30? The answer is both, depending on the reference frame. Is the train completely inside the mountain at any one time, or is it not? Both, depending on the reference frame. The reference frame will tell you that simultaneously both ends in the mountain or not depends on the reference frame. So they're both true. There's no absolute to which event came first if they're connected by a tachyon gun. There's no way to say which one came first. It depends on your reference frame. Some of the things that we just naturally assume about space and time are no longer true in relativity. All of these descriptions are correct. There are some descriptions that aren't correct. For example, the fact that the train never went in the tunnel. That's wrong. Whether the entire train is in the tunnel simultaneously depends on the frame of reference. Tricky stuff. And you'll find a lot of elementary books written for the layman that get it all screwed up. They know you're thirsting to understand relativity theory, and so people write little quickie books, and they explain things to you. And normally they don't include it. I'm including it at a higher level than they usually do. In fact, I think a lot of the authors don't really understand it. I've published several articles on this in professional journals just to help all those people who are confused on it. Let me go on. Because now the issue of Einstein came up with this idea that the speed of light would be the same in all reference frames. I'm going to give you a little bit of the technical background on that. I said that suppose light is coming towards me. How do I measure the speed? I measure it when it's here. That's time. Time and location, an event. Then the light goes here and it's here, an event. I look at the distance. I look at the time. That gives me the velocity. Velocity is the distance per time. I measure the speed of light. Now I do this from a moving reference frame. And three things happen that confuse everything. The first thing that happens is the light's still coming. You know, so it was a laser set up on the end of the bench there. It's still coming. But now I'm not going to measure it standing still with a standing still ruler. I'm going to measure it with a moving ruler. So what's going to happen? My moving ruler in the lab frame is going to be shorter. Here's the little ruler. And when the light hits it, it'll hit here and then here. But in the moving ruler frame, time is dilated. So the times are different. Not only that, but you lose simultaneity. So the relative time changes. This is not that hard to do. There's something called the Lorentz transformation, which I haven't bothered doing. I could give it to you, and those of you who like algebra would have fun with it. And I can write it down. It's not that hard for the time and the location of events and how that changes in different reference frames. But I'm not going to do that right now. I'll be happy to do that before class or in discussion or something like that. Instead, I'm going to give you the answer, the one that Einstein derived based on these three effects. And here it is. It says, what velocity will I, something is coming towards me. It could be light. It could be a bullet. It's coming at me with a velocity v1. And I'm moving towards it with a velocity v2. So here's a bullet coming at me at 10 miles an hour. I'm moving towards it at 1 mile an hour. You'd think the velocity in my frame would be, it's 10 plus my 1 would be 11. You think it would be v1 plus v2. So this is the velocity you expect. It's v1 plus v2. This is just logical, isn't it? Isn't it obvious? Well, it's neither logical nor obvious. But it actually is pretty true. It's one of the things you study in elementary physics before you get to relativity theory. It is approximately true, it turns out. But if this were true at all velocities, I'd run into trouble if I were moving near the speed of light and the light was moving at the speed of light. We run into each other. It would be at about twice the speed of light, and Einstein didn't like that. He invented relativity theory to accommodate that. And when he did it, the equation he got wasn't this, the obvious equation, but it had an extra term in it. 1 plus v1 v2 over c squared, where c is the velocity of light. It's actually not the velocity of light. It's the velocity of light in the vacuum. And in fact, it's not really the velocity of light in a vacuum. It's the Einstein constant. The reason I say this is everybody refers to the velocity of light as if light has some special role. Light doesn't really have a special role. This number comes in, the Einstein constant. And it turns out that if photons are massless, they will travel at the Einstein constant. That will be their velocity. So we call it the velocity of light. If you didn't understand why I just told you that, don't worry about it. You can listen to it over again in the webcast. So just think of it for now as the velocity of light. I'll come back to this a few times. Now look what happens here. Suppose v2 is equal to c. That is, I'm looking at a light beam coming at me. And here I am measuring it. I'm moving at some velocity, well, I don't know, I guess I had v1 equal to c. Right? v1 was the speed of the light. It's coming towards me. I'm coming towards it with v2. So what will I measure according to the Einstein formula? It's not really that complicated a formula. Let's see what it is. The velocity I will get v is equal to v1, which is c, plus v2, which is my velocity. I'm not going to tell you what it is, divided by 1 plus v1, which is c, v2, over c squared. So that's the answer. Not a very elegant answer. I'm not going to require that you follow this simple algebra, but everyone here can follow it well within your capabilities. I'm just not going to ask you to do it because you're not in love with math like I am. So let me, well, there's two factors. Let me cancel this factor of c. Let me multiply the numerator and denominator by c. Okay? And so I'll write this as c plus v2 times c. And this I'll bring the c inside, and inside it becomes c plus, well, that cancels the extra c on the bottom here. So that'll be v2c over c, and those cancel. So I get that. And then, so just working out the algebra, now the c plus v2 cancels the c plus v2, and I get c. Let me tell you what I just calculated. A beam of light is coming down this table. If I sit here on the table and measure its velocity, boom, boom. Okay, it went 1 foot in 1 nanosecond. That's 3 times 10 to the 8th meters per second. Ah, it's traveling at the speed of light. I should have known that. It is light. Okay, good. Now I'm going to do it, but my ruler and my clocks are going to be moving in. We're going to be moving at this velocity v2. So it's coming at c. I'm moving at v2. And I say, what velocity will I get? And instinctively you say, well, you get c plus v2. But if I use the Einstein formula, and I put in that v1 is c, and I don't put what v2 is, I'm keeping that a secret, I work it through a little bit of algebra, I get, oh my God, I get c no matter how fast I'm moving. No matter, this is what Einstein designed the theory to do this. The fact that he was able to design a theory to do this is his greatest genius. You'd think if you design a theory to do this, you mess up everything, like tunnels and trains. And it turns out you don't. You just have to think about time in a new way. So this is the velocity equation. You don't have to know it. But I do want you to know that no matter how fast you're moving, the speed of light will always be the speed of light. The direction might change. If the light's coming straight down and I'm moving, then the light will look like it's tilted. Because as it's coming down, I'm moving past it. But its speed, it turns out, is still the same. The speed of light is the same in all reference frames. That's not a surprising result because that's what Einstein wanted to derive. The fact that he could derive that he could make a self-consistent system, is amazing mathematically. It leads to time dilation and length contraction, which we observe experimentally. One of the great predictions. Now, his second paper on relativity was another step which was almost, I don't know how to him it was obvious he had to do something about ordinary physics mechanics. And this is going to lead us in a few steps to the famous equation of relativity theory E equals mc squared. Based on what we've done so far, speed of light is constant, no contradictions with tunnels. You can get to Alpha Centauri or get to a star 7 light years away, and you'll be 1 year older. It's all hanging together. But he recognized there was still a problem. And I'm just going to say qualitatively what the problem is, again, without doing the math, because if I do the math, I spend a whole lecture on it to a physics, and you don't need that. I want you to understand the effect. Imagine I'm sitting here, and two things go out with equal velocity. Now I measure this from a moving frame, and here's this thing going by, and it blows up into two pieces. And you think the two pieces are such that this part would be going out that way, this part would be going out that way. Together they would have, in Einstein's worry, this was the conservation of momentum, something we just touched on, the fact that the mass times the velocity has to be the same for the two objects that come out, they have to be equal and opposite. Einstein concluded that that wouldn't work. That because of the velocity equation, the two things would not be coming out in a different reference frame with canceling velocities. And so he would lose all of physics, all the physics based on the fact that when you push on something, you accelerate it according to Newton's laws. So at this point, if I had been smart enough and had been born to conclude that I could come up with a self-consistent picture of time and space, at this point I would have said, whoops, I lose all of physics. Okay, that theory was wrong, so let's look for something else. Einstein didn't do that. His reaction was, have to change physics. What did he have to change? He figured out that the thing he had to change was our idea of what is mass. And with a few lines and a few simple steps, the hard part was recognizing you got to change the physics. The thing he found he had to change was the concept of mass. So what he deduced on this is the following relatively simple equation. That if you have an object at rest, and you measure its mass, how do you measure its mass? Well, you could weigh it, or you could push on it and see how fast it goes. If an object is at rest, he said the mass now, at rest, we're going to have to give it a special name. We'll call it, cleverly, the rest mass. And we'll call it m0. Now physicists pull a trick on you, and this is absolutely standard. We start, because of the confusion, because this mass is going to change when the object's moving. We now refer to the mass of an electron as having a certain value, so many grams. What we're always referring to is the rest mass. When they say a particle has a mass of 9.3 times 10 to the minus 27 grams or something like that, what they're referring to is not the mass of the particle. They're referring to the rest mass, just by convention. If you come across people saying, for example, that various particles have certain masses, that's the rest mass, because the mass changes as it's accelerating. How much does it change? Well, here's one of the wonderful, glorious things of relativity. Suppose I have an object moving at velocity v, and I express it in terms of light speed, beta. So it's moving at 99% the speed of light. Its mass changes. It gets bigger. How much does it get bigger? Here's the great result. It gets bigger by a factor gamma. The mass is equal to gamma m naught. I want you to know that. We have three things. Time slows down, the length contracts, both by factors of gamma. The mass has the same factor, gamma. Here's the list of gammas. At 99% the speed of light, gamma is 7. That means if you're going 99% the speed of light, you are 7 times heavier. Lorentz, when he invented his atom smashers, ran into this problem. He had this nice thing where the things were going faster and faster and faster, and they were bending in the magnetic field to go in a circle, but as they went faster, they got heavier, and they didn't bend as much because they were so heavy. This effect was seen when Lorentz was building his cyclotrons. They get heavier by this factor. Now, the effect can be big. You're getting squished, your time is slowing down, and you can get very massive, hundreds of times, thousands of times heavier, which means you really, you may never reach the speed of light. And I'll show you why you can't. When you get to the speed of light, your mass becomes infinite. So he worked out this mass thing, and then he worked out the energy, and he came up with a remarkably simple energy equation. Remember the old energy equation? Something's moving, it has energy of motion, and the energy was 1/2 mv squared. Right? Now that m was actually the m naught. I didn't tell you at the time, because we hadn't talked about mass increase. In fact, the remarkable thing is for everything in physics, you just assume the mass never changed. It was always the same. But here, this equation, he had to rederive it. It turned out he got, again, a truly remarkably simple answer. When he rederived this, by going back and taking into account this velocity equation and the way things change, he got the following answer for the energy. So this is the old answer. His new answer was that the energy was equal to mc squared. Most famous equation of the 20th century. Now, this was the total mass, so I should really write this as gamma m naught c squared. Now, there's something funny here. E equals mc squared, that doesn't look like it depends on velocity, right? Think about that for a moment. The energy doesn't depend on how fast it's moving? Or am I fooling you? I'm fooling you. Because the mass depends on the velocity. So if you're going faster, you have more mass, that means you have more energy. How can that, but wait a minute, we know this is true. It works for roller coasters and cars and bullets and rockets and everything. How could that not be true anymore? And it's very different. The difference between 1/2 mv squared and gamma m naught c squared. C is huge compared to most velocities. How can anything have that much energy? Well, the answer was obvious to Einstein. Now I'm going to do a little bit of math, which you are not required to follow. I want you to understand the answer. And some of you, even the math majors, may be surprised at some of the shortcuts and approximations I make. But I'm going to take Einstein's answer, E equals gamma m naught c squared, write that as m naught c squared, and in the bottom put the square root of 1 minus beta squared. That's the gamma factor. Beta is v over c. So this is Einstein's equation written out a little more detail. Now I'm going to consider small velocities, the kind of velocities we have in a typical physics demo, except when we're using a laser. At small velocities, beta is very small. This light speed number at small velocities is tiny. You know, in laboratory things, v over c, you know, if I'm going 3 meters per second, then beta is 10 to the minus 8. Because the speed of light is 3 times 10 to the 8th meters per second. So beta is tiny. It's a small number, 0.00001. It's a tiny number. If I take the square root of a tiny number, it's relatively easy to show. I'll do this over here. This is completely unrequired. The square root of 1 minus beta squared is very accurately given, although not completely, 1 minus beta squared over 2. If you don't believe it, try it on your calculator. Take a beta equal to 0.001 and plug that in there, take the square root, and then do this, and you'll find the answers are about the same. The reason that's true is because if you take 1 minus beta squared over 2 and you square it, you get 1 minus 2 beta squared over 2 plus beta to the fourth over 4. And this number is, if this is tiny, beta to the fourth is really tiny. You ignore that. This becomes 1 minus beta squared. So if you square it, you get the right answer. You didn't follow that, ignore it. But that's why it works. You can also use the Taylor series if you have studied calculus and derive it that way. That's a hard way to derive it. So this is approximately true. So let's put that in over here. So this is going to be mc squared m naught c squared. Again, if you want to go to sleep now, you're welcome to do that. You don't have to follow this. I'll wake you up when we come to the end. And instead of 1 minus beta squared here, I'll have 1 minus beta squared over 2. We're getting there. Now let me show you another approximation that you don't have to know. If I have 1 over 1 minus a small number like beta squared over 2, this is approximately equal to 1 plus the small number beta squared over 2. Don't believe it? Try it on your calculator or your computer. It's remarkably good if beta is a small number. Why does it work? For those of you who care, if I cross multiply these, I get 1 is approximately equal to 1 minus beta squared over 2 times 1 plus beta squared over 2. And that's obviously not true. But multiply these things together, the cross terms cancel. You get that this is 1 minus beta to the fourth over 4. And beta to the fourth is so really tiny compared to beta squared that this is a pretty good relation, as you can check with your calculator. So you don't have to know that. But it means I can take this 1 minus beta squared over 2 and put it on the top. So this is equal to m naught c squared times 1 plus beta squared over 2. Right? Continue on with the math you don't have to know. But it may amuse you. It's probably more fun than surfing the web if that's what you're doing. You don't get to see this very often. Maybe the only time in your life you get to see the derivation of the energy equation. OK, now I'm going to multiply this out. And I get that this is equal to m naught c squared plus m naught c squared times beta squared over 2. And now I've run out of space. Let me slip this up here and continue. I get that the energy equals m naught c squared plus m naught c squared times 1/2. Let me put 1/2 in front. That's the 2 in the bottom. And then I have a beta squared. Now, beta was v over c. Remember that? Beta equals v over c. So let me put that in here. And this is m naught c squared plus 1/2 m naught c squared. And beta squared is v squared over c squared. The c squares cancel. And I'm left with the equation. This is what I wanted to derive. This is the key equation. Wake up now. That at low velocities, the energy, according to Einstein, is m naught c squared plus 1/2 m naught v squared. In other words, the energy from Einstein is equal to the old energy, the one that we had before, 1/2 mv squared. Here it is, this old one. It's the same equation, but it has this thing added in, m naught c squared. This is called the rest energy. Now, if you're using energy in an equation, and you have you have a big battery, and you're asking, well, the battery bounces off something, there's so much energy, but the energy of the battery never changes, you don't have to consider that. It doesn't change, so you don't worry about it. If the rest energy never changes, you can ignore it. Newton, in doing physics, the rest energy was never changing, so this was the only part that he needed. But now we learn there's another part. So here's what I want you to remember from all of this. in the theory of relativity, there are two parts to the energy. One is exactly the same as Newton, at least at low velocities. 1/2 mv squared, m being m naught now. But there's a new term we call the rest energy. And since that doesn't change, you can ignore it most of the time. But not all of the time. Because this really is energy. And because it really is energy, you could turn it into useful energy. You can get rid of it. That's what happens in the PET scan. PET, positron emission tomography. What you're doing there is the positron comes out. It's antimatter. It hits an electron. It has rest energy. The electron has rest energy. They come together, and they turn into two particles of light. A particle of light, it turns out, is essentially pure kinetic energy. It has no rest energy. As I'll show you, the rest energy of a photon is 0. It has 0 rest mass. All the energy comes out can be turned into heat. You can take all of the energy of a positron and an electron and bring them together. It's called annihilation. When you do that, all of that rest energy gets turned into energy that can be converted into heat. This is, of course, the standard engine being used by most science fiction spaceships. Well, the antimatter drive. Why do they do that? Well, if you take fission, for example, you get typically, 1 MeV per nucleus, MeV being a unit of energy that we touched on briefly. If you could turn all of the energy into matter, then instead of it being 1,000,000 times greater than gasoline, it's 1,000,000,000 times. You get another factor of 1,000 by using up that energy. So an antimatter drive is 1,000 times better than a fusion bomb or controlled thermonuclear fusion. And so that's why all the science fiction uses it. You get a factor of 1,000. That's a lot. You get it by converting the rest energy into heat, which is used to push things out the back of the spaceship. So that's the key. So here's what I want you to know. I want you to know that in relativity theory, in addition to the usual equation, at low velocities, the same as Newton's equation, you have another term, which is the rest energy. This equation is only true at low velocities. In making the approximations, I had to assume that beta was very small. The exact equation is here. Well, this is the energy. This is the exact equation. E equals mc squared equals gamma m naught c squared. That's the exact equation. But the approximate equation, which is the only thing we use when we're down at low velocities, is that equation. Now, the next step in Einstein's train of thought actually took, there are a couple other things here. The relationship between energy and mass, this thing here. Basically, all energy change is essentially a mass energy. What happens as you get a particle going faster and faster? Suppose I take you and I start sending you near the speed of light. What happens? Well, your mass goes up by a factor of gamma. At 99% of the speed of light, gamma is 7. There it is, right up there. At 99.9% of the speed of light, gamma is 22. Your mass is increasing by a factor of 22. At 99.999, the speed of light, your mass is increasing by 224. Suppose you do go to the speed of light. What does your energy become? Gamma, m naught doesn't change. But gamma times m naught becomes infinite. The energy to get you up to the speed of light is infinite. What does infinite mean? Well, it's more than all the energy in the observable universe. Just to get you to the speed of light, just to get an electron to the speed of light, would we take more than all of the energy in the entire universe? That's why you can't go to the speed of light. You don't have enough energy. There's the equation. E equals mc squared. The m is m naught times gamma. Gamma goes to infinity. That's why you can't go to the speed of light. Now, wait a minute. There are things that go the speed of light. They're photons, right? We talked about photons. They're the particle-like nature of the wave particle. They go the speed of light. How do they do that? Well, here's the real irony. If you can be at rest, you can never get up to the speed of light. This is weird. If you're traveling at the speed of light, you can never slow down. That's kind of odd, isn't it? Let me look at that. In a photon, I said to you when we were doing quantum mechanics that these packets of quantum mechanics have energy in them. And the energy depended on the frequency. E equals h times the frequency. This was the equation for the energy when a photon is absorbed. So they do have energy. Now the Einstein equation is still correct. So let's say this then is, this is not 0, that's a real number. Let's set that equal to mc squared, which will set equal to m naught gamma m naught c squared. So this is the energy, and according to Einstein, this is what it is. But this is infinity. So isn't the energy infinity? Well, there is a logical solution to this. It looks like we're getting infinity, but that's only because infinite times anything is infinite, right? Well, no, actually, not infinity times 0. What is infinity times 0? Well, that could be anything. So the photon must have a 0 rest mass. What is the rest mass? Well, it's the thing that goes in this equation. What happens if we bring the photon to rest so that its velocity is 0? Let's take a photon at rest. We slow it down. What happens? Then the energy is equal to gamma m naught c squared. This is equal to 0. This is equal to 1. C squared is a big number, but that's 0. The energy is 0. If you slow it down, you get 0 energy. In fact, if you slow it down to any velocity, so gamma isn't infinite, any number here, I don't care whether it's 3/4 the speed of light or 99.9, if this is not infinite, then it times 0 is 0. So if you slow the photon down, it has 0 energy. That doesn't mean you can't slow it down, but how do you detect something that has no energy whatsoever? It has no mass and has no energy. It fundamentally just doesn't exist. So here we have this fascinating new insight into the way the world works. Yes, you can go the speed of light, but then you can't slow down. You can go slower than the speed of light, but then you can't get to the speed of light. Raise the issue of tachyons, which let me not go off on that just yet. We did talk about tachyons. Tachyons, it turns out, are these particles that go faster than the speed of light. I talked about them last time. Not last time. Last time was an exam, but the time before last time, when I explained to you that tachyons can exist. They do violate my sense of causality, my sense of whether I have free will, but that doesn't mean that I'm right. It could be an illusion I have. So some people who don't believe they have free will are looking for tachyons. I guess they have no choice, do they? Anyway, they're looking for tachyons. And if you find one, it turns out tachyons have another peculiar property. They have what we call an imaginary mass. That's okay. Imaginary in math doesn't mean doesn't exist. Imaginary is just a bad choice of word. That means it's not part of the real number system. It's part of the complex number system. Again, you don't have to know that. Here's what I want you to know about tachyons. Tachyons can exist, assuming you don't worry about free will. They go faster than the speed of light. They get more energy when they slow down. In other words, they go from going twice the speed of light to near the speed of light. They get more energy. Weird. You can never make them go slower than the speed of light. You can't make them go the speed of light. They must always travel faster than the speed of light, and the faster they go, the less energy they have. You can see why people are fascinated, why people would love to find such a thing. And all you got to give is your own belief in your free will. Gee, but it would be so great to find it. Tachyons are weird. They're part of science fiction. And I have, I think, freely, of my own free will, chosen not to look for them because I suspect that they don't exist. What about neutrinos? These are a really interesting case for the last few years. People believed until recently that this mysterious particle called a neutrino, which we haven't talked about, we'll be talking about more about it very soon. We're getting into this kind of physics. Neutrino is a particle that comes out when you have a nuclear decay. For example, if you have tritium, and it decays into an electron in the leftover nucleus. But a mysterious particle comes out called a neutrino. And the neutrino is interesting because it's unaffected by electromagnetism. It's, because of that, it passes right past electrons. And for the most part, doesn't see them. It penetrates and goes through things. And until recently, we thought neutrinos were also massless particles, that they also have no mass, that they were like photons. And just in the last 10 years, in a series of experiments that indicate that neutrinos have mass. The first of these experiments, this is really interesting. How do you tell a neutrino has mass? The answer is, if the neutrino changes, then it must have mass. Well, what does that mean? Well, what happened, what we saw is the neutrino would actually decay. It would change into another neutrino. How long did it take to do that? Well, it depended on how fast it was going. But in its own reference frame, if the neutrino is going near the speed of light, its time slows down. So any natural change it makes slows down too. If it's really going the speed of light, it slows down so much it couldn't possibly decay. Its time would be slowed down by infinity. Photons don't experience time. If a neutrino was really going at the speed of light, it couldn't change. It could disappear, but it couldn't change. It couldn't change into another particle. So, interesting thing. Neutrinos now, we know a lot about them. They don't quite go at the speed of light. There are several different kinds of neutrinos, at least 3. And at least 2 of those don't go at the speed of light, but they go very, very close. So neutrinos are no longer massless. So we have photons. Those are massless. They go less than the speed of light when they're going through glass. But going through glass, it gets very complicated. The equations I've given you here are the equations for when it's going through a vacuum. When it's going through glass, you have to consider all the glass atoms. So the fact that it's slowing down doesn't really violate causality if you're going through glass, because what's really happening is the photon is scattering from one atom to the other. So when we say the speed of light, we mean the speed of light in a vacuum. Does a photon really have 0 mass? Maybe we're wrong, like on the neutrino. The fact is we don't really know that it goes, we don't know where the light goes at the speed of light. That's why I call the speed of light the Einstein constant. All we know is it's very, 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 very close. And there are experiments, astrophysical experiments that people have done to see whether it really goes at the limiting speed. Could the photon actually change with time? Just in a vacuum. There are some theories of this. It's called tired light, where a photon loses its energy as it's going along. It's changing with time. In that case, it wouldn't have zero energy. It would be interacting because the vacuum is not, space is not a truly empty. The last thing I want to talk about is this weird thing called binding energy. And this is getting somewhat abstract here. Suppose I have a nucleus, and I pull it apart. I have 2 things now. I can weigh this one, get its mass, weigh this one, get its mass. Suppose I compare it to the mass I started with. So I have this one mass, and I pull it apart, and now I have 2 of them. I gave you a hint in the way I said it. I have this mass, and it's held together with these gluons that hold it together. And then I pull it apart. I'm putting energy into it to pull it apart. And then they're just sitting there. What happened to my energy? Well, the fascinating fact is my energy went into the mass of these particles. They now weigh more than they weighed when they were together. If I take helium, 2 protons and 2 neutrons, and I pull it apart into those 4 particles, I put that energy in, pulling it out. I now weigh those 4 particles. It weighs more than the helium did. You may have noticed in chemistry courses, those of you who have taken it, if you've ever looked at this, you look at the weight of a helium atom, and it is actually less than the weight of 2 protons and 2 neutrons. That's because when you pull the protons and neutrons out, you have to put energy in. That's a strange effect. It's called the binding energy. The energy that you have to put in to separate it is the binding energy. And that means you increase the mass, which means the original particle had less mass. I mean, it consists of 2 protons and 2 neutrons, but it has less mass than the sum of 2 protons and 2 neutrons. Really strange. What do I want you to know about binding energy? You know, I think I'll skip that. I think you don't have to know binding energy. Why? Because this is, again, one of these, every time I give you an abstraction, that twists your mind, there are just too many things. You can't keep them all together. Each one is so counterintuitive that if you walk out of your lecture today with 17 things that don't make sense, you'll just walk out saying, I can't understand it. So I've outlined the things I want you to understand. Now, on Thursday, the reading is due. That covers relativity. We're also going to do on Thursday general relativity. And then general relativity will lead us into understanding cosmology and the universe.